Okay, let's get started. Okay, last time we were talking about implicit differentiation. Basically finding the derivative when the definition of the function is not explicit. Like I can't talk about one variable completely in terms of the other variable, but the relationship between them is kind of mixed up. However, we still want to be able to do calculus in this case, and implicit differentiation is how we did it. And it's just really an application of the chain rule. And we ended with an example last time. Where basically I said our only kind of hope of being able to talk about the derivative in this case was to do implicit differentiation. This was the volume of Descartes graph, looks like that. And we couldn't actually solve for y to get it as a function of x to be able to find the derivative here, but we could find y prime in terms of both x and y. We found that y prime was, well, I don't have the answer here. What did we say? Yeah?
Negative 2x over 7y to the 6 minus 2.
Okay. So we did implicit differentiation, we figured that out. Now, you might be wondering, what good does that do me if I don't know exactly the y value? It turns out that actually does a lot. There are many cases in which we cannot actually find a function, a nice definition that will tell us about all points along a function at once. However, not in this class, but there are other classes devoted to figuring out what functions behave like on a point-by-point basis. So you'd be able to approximate any coordinate along this function that you may want. So a class like numerical analysis will go into something like that. So whereas I can't, for a given x, I can't tell you exactly what the y is, but via various methods, I'd be able to approximate what the y would be within any degree of accuracy I might want. So if you want to be able to do it within 15 decimal places, we can do that. Within 25 decimal places, we can do that. In reality, we never really use the exact answer anyway. We're always kind of working with approximations, and so this is still a useful thing to be able to do. Yeah.
Is this it? We're not learning anything new. This is just like extended applications, right?
Yeah, this is, we are going to learn a new technique, but it's still applying the same thing.
Wait, so is that, do we have to remember that for the exam as well?
No, I don't. Yes, implicit differentiation, what we're doing, what we did last class is on the first exam. So yeah, so that is the case. We found the derivative, it was this guy, and it's still useful because in general we can approximate on a point-by-point basis. So if we happen to be interested in a specific point, we can deal with it, and this allows us to do calculus at that specific point. I want to actually continue with this example a little bit and actually focus on one point. Let's say I pick a random point here, 2, 1. You can verify that that point is actually on this curve. If you plug in x equals 2 and y equals 1, you would get 4 plus 1 is 5 minus 2, which is actually 3. So by inspection, we can see that this point is on the line. So let's say I were to ask you a follow-up question here. So phrase that as a question. What is the equation of the tangent line to the above curve at the point 2, 1? Okay, how would we actually go about doing that? Yeah?
You would use the derivative as the slope of the tangent line.
Right. The derivative gives us the slope of the tangent line, so what do we do with this here?
And you could plug that point into y equals mx plus b using derivative of the m.
Right, so the derivative is going to give us the m for the tangent line, which is this formula. Knowing the coordinate that I care about, I can just plug these guys in. I would plug in all the x values to be 2, all the y values to be 1. Ultimately, I'd end up with minus 2 times 2 over 7 times 1 to the 6 minus 2. That gives me minus 4 over 5, and that will be the slope of the tangent line to this point. Now, we already know the point. That is 2 comma 1. So now basically I can get the tangent line by y minus y1 equals n x minus x1. So it's y minus 1 equals minus 4 over 5 x minus 2. So that is a straight line with slope minus 4 over 5. So if we were to actually amend this picture here, our tangent line would be a guy that's passing through there. Obviously has a negative slope. You'll realize that the y-intercept will be positive here. Take minus 4 over 5 times minus 2, you get a positive number. You would add 1 to both sides. So that will be the intercept here, but that is the equation of the tangent line. So we can determine points of interest. This one was nice. We had some whole numbers that fit in here. Otherwise, we could technically approximate this point with any degree of accuracy we want for any arbitrary point along this curve, and we can actually create tangent lines there. And remember, the point of a tangent line is to approximate a curve locally, which means when we start zooming in here, if we zoom in far enough, the equation of the tangent line and the equation of the function itself won't actually be that different, which means there are contexts in which, yes, we care about working with this, but it would be equivalent to working with this. And that's really nice because we know a lot about straight lines. Being able to work on this and by extension study this is a very useful thing to be able to do. And calculus is one way that allows us to do this. So functions themselves can be messy in how they're presented to us, but with implicit differentiation, we can do calculus analysis on curves by using the chain rule. I want to do a few more examples here just to get back into the groove of doing this, and then we'll talk about one new differentiation technique. Which we'll talk about one of, at least, that will extend to one of the bonus problems on the test. You won't really need it for the test, but we'll talk about it here. So what we're going to do, just a few more examples of finding y prime. Given that expression, well, C is somewhat different. Here, I'd like you to find these two guys, dV, dP, and dP, dV. If P plus 5 over V squared times V minus 0.03 equals 0.7. I'm curious to know, does this look familiar to anyone? This expression, this last one? you seen it before, seen something familiar? Yeah?
Does that have to do with chemistry?
It has to do with chemistry.
Van der Waals equation?
It's Van der Waals equation for a specific gas. So it turns out when studying specific gases, and we're studying the pressure and the volume of these guys, this happens to be a relationship that the chemists came up with, probably after inhaling too much ammonia gas or something. This is just how the relationship was developed. Pressure and volume is not, you can't just say, oh, pressure was this in terms of volume, or volume is this in terms of pressure. It came to them as this jumbled equation here. But, of course, we do want to be able to measure things like how fast will a volume change respond to a pressure change, or vice versa. How does affecting the volume affect the pressure, etc. And we might want to do a calculus analysis of this equation. So this is actually, yes, it's Van der Waals equation. For a specific gas. Right? Where here your P is representing the pressure of the gas and your V is representing the volume of the gas. Turns out those two quantities will obey this expression. So this is just a real world example of why something like implicit differentiation would be important. Because sometimes our relationships don't come to us in the neat packages like y equals x squared. Sometimes it comes to us like this. But we'd still want to be able to talk about calculus with things like this. Anyway, just let's go through the computations here. Theoretically, there's nothing else to talk about. It's just a matter of getting used to the process. So, A. Given this guy, how do we find y prime? What do we do? Yeah?
We did derivative of everything.
Right. Differentiate both sides, and differentiate the sum is just the sum of each term. So we go one by one and differentiate everyone. Derivative of this,
Oh, 8x
derivative of this,
plus 2x y prime plus 1.
right? Notice she applied the product rule here. She differentiated the y function, left the x function alone, gave her this, plus differentiate the x function, leave the y alone, gave you 2y. So that was the product rule there. That is the derivative of the second term. Third one,
Minus 6xy squared minus 3x squared 2y prime 6x squared y prime.
right? Again, apply the product rule. Of course, you'd open parentheses to apply the product rule, and the negative sign that was in front here would be distributed. So we have two negatives here. Derivative of 4,
0,
0. Derivative of 7,
0,
derivative of this.
negative 1 0.
So that is the first run through with the derivative. Now we actually want to find y prime, but now it's just a matter of isolating that y prime via algebra. So we would find y prime and take out all the common terms. So 2x gets rid of that term, minus 6x squared y gets rid of that term. That was the only one that had y primes in it. So now I'm going to move everyone else to the other side. Minus 8x plus 6xy squared. And that's everyone. And so now I can solve for y prime by just dividing both sides by this. And we have a little bit of a complex fraction issue going on here with the 1 over x. We could simplify that by just multiplying by x over x. So a slightly nicer version would be something like minus 1 minus 8x squared plus 6x squared y squared over 2x squared minus 6x cubed y. And that is our group. Yeah.
Can you explain the differentiation of the third term there, minus 3x squared y squared, just in terms of like the...
Oh, this
yeah,
here?
Yeah.
Okay, so if we're looking at the derivative of 3x squared y squared. Basically, this means it's 3 times the derivative of x squared y squared. So that's 3 times, differentiate this one, leave that one, plus, now we leave the first one, differentiate the second one, derivative of y squared is 2y prime. Because remember, our y is like, there's a hidden function there, it's like an f of x. So you have to do the chain rule, bring the 2 down, multiply by derivative of the inside. And so ultimately when you multiply this out, you get 6xy squared plus 6x squared y prime. And then, because there was a negative sign in front of it, that negative gets distributed and then this.
You forgot one term, you forgot 2y to bring on the other side.
I did forget the 2y. And I was going crossing out here to make sure I didn't remember anybody. So we have to bring over the 2y, that'll just add an extra term here. So it's a minus 2y, which would give us a minus 2xy. Any other questions on that one? Okay, what about the second one? How do you differentiate something like that? Differentiate this. What is the derivative of e to the x plus y squared? Yeah?
E to the x plus y squared times 2y prime. So the derivative of e to the x dx, that all stays the same, and then you multiply by the derivative of x plus y squared.
Right, so it's the derivative of the power times the original function. This is how we differentiate exponentials. What's the derivative of the power?
2y times y prime.
Plus 1.
Plus 1.
Oh, plus
There's
one,
the x
sorry.
here. So derivative of the x is 1 plus 2y prime is that, right? Because we know the derivative of e to anything is the derivative of the thing times the original function. Okay. So now we can, that's the derivative of the first term. What about the second term? How do we differentiate ln of something?
It would be 1 over x plus y times 1 plus y prime.
Right, so it's 1 plus y prime over x plus y. Right? And that's because we know the derivative of ln of something is just the derivative of the thing divided by the thing itself. Right? Derivative of 3? 0. And so now again, we want to isolate the y primes. So I'll start to break these out of the parentheses. Distributive law here. Plus, I just split these fractions here. And again, isolate the y primes. That'll be 2y e to the x plus y squared. Gets rid of that term. Plus 1 over x plus y. Gets rid of that term. These other two terms are going to move them over, so this is minus e to the x plus y squared. Gets rid of that term. Minus 1 over x plus y. Gets rid of that term. We've accounted for everybody. And so now the y prime is just going to be this divided by that. And we can multiply this by x plus y over x plus y, just to simplify it a little bit. And so this would be minus x plus y, e to the x plus y squared minus 1 over 2 x plus y times y e to the x plus y squared plus 1. Let's see derivative there. Questions on that one? Again, moral of the story, don't forget the old rules. All those rules that I always ask you to memorize and regurgitate on quizzes, they will always apply. Exponentials, we know how to differentiate those. Logs, we know how to differentiate those. Just because x's and y's are mixed up, it changes nothing. The rules still apply, the same rules. Now, what about the part C? Now that's an interesting one. Let's look at d v dt. What does that mean? How would I go about finding that derivative? What does it mean d v dt? Yeah?
It's same as dy over dx, so p would be the x here.
Right, essentially, exactly. Right? So this notation tells you who you're thinking of as the independent variable, that's always going to be at the bottom, and who you're thinking as the dependent variable, which is on the top. Which means, ultimately, when you're trying to do implicit differentiation, whenever you differentiate a function of p, you don't do anything. If you differentiate a function of v, you have to multiply by v prime. Or literally with any other letter other than p, you have to multiply by its derivative. Okay? So this is just basically saying what the rules are, right? So this would be equivalent to someone saying v prime, but that is of course kind of vague if you don't know what the independent variable is. You can also think of this as v prime of p. So you know that I'm thinking of p as the input, the v as the output. And so that means whenever I'm differentiating a v, I have to apply the chain rule. If I'm differentiating a p, well, it's kind of like differentiating an x. So that's what this notation means. So sometimes we want to think of the volume as the dependent variable, meaning we're manipulating pressure and we're seeing how volume reacts. Versus sometimes we want to think of, let's manipulate the volume and watch how the pressure reacts. And these guys are just those two different points of view. It is also worth mentioning that in the same way I asked for dy dx, in some contexts I might want to know about dx dy. And again, this shouldn't be confusing, it's just noticing who you're thinking of the input versus the output and how the chain rule would apply in that case. So in this case, dv dp means our independent variable is the p, so that's like the x that we've always been doing, and the v would be like the y. So going through here and differentiating this, again, doesn't matter what topic we're in or how far we've gone or how complex the functions get, the rules always apply, the basic rules always apply. So if you want to know how would I differentiate this, it's the same as how would I differentiate something times something, always the same way, product rule, unless one of them is a constant, which in this case it's not. So I would go through and I would apply the product rule here. We're going to differentiate this, leave that alone, plus differentiate this and leave that alone. With the awareness that whenever I differentiate a p, I don't really have to do anything, just apply the rule. If I'm differentiating a v, I have to multiply by a v prime. So this would mean differentiating the first one would be 1. How would I differentiate 5 over v squared? Yeah.
Negative 10.
Negative 10v what?
I mean, I took the v square up and made it.
Right, so you're thinking of it as 5v to the minus 2,
Yeah.
and what would its derivative be? Negative 10.
Negative 10 v. Negative 10 over v.
Well, what is the rule?
Oh yeah, wait. That's n minus. Negative 3.
-3, right? Subtract 1 from the power.
Yeah.
Again, because p is our independent variable, this guy I think of as a function of p, so I also have to multiply by the v prime, by the chain rule. So that's what's going to happen here. So I just rewrote this by bringing it up and using the power rule, and then knowing that my p is the independent variable, this guy I have to apply the chain rule. Now I leave the second part alone, plus now I leave the first part alone, and I'm going to differentiate the second part. And what's the derivative of the second part? Derivative of v is going to be just v prime. Derivative of the 0.03, 0, constant. Derivative of 9.7, 0. And now, again, the goal is to find the v prime. And from here on out, it's just a matter of algebra. We've already done all the calculus. It's the first step. The algebra is most of the work here. So expanding these parentheses, 1 times everyone in there. This times everyone in there. V prime. And then that expands that. Here I would have plus p v prime. And here I would have 5 over v squared v prime. So then, again, I'm going to isolate the v primes. It's minus 10v to the minus 2, minus 0.3v to the minus 3, plus 5v to the minus 2, plus p. All of that. Then I'll bring everyone else to the other side. 0.03 minus v. Everyone accounted for? I think so. And then I would have v prime is just going to be 0.03 minus v all over. Well, these guys I can combine. That's just minus 5v to the minus 2 minus 0.3v to the minus 3 plus p. That is my derivative of v with respect to
Plus 0.3, yeah.
where? This plus 0.3 where?
That would be plus.
A negative 10 times a negative 0.03.
Because slider times slider.
Oh, here. That's a plus? That's what you mean? Yes, that is correct. Let's see. So that would be here, and that would be
Oh shit. So
This is
would
the
it
algebra. So what's the algebra? Yeah.
be, would it be simpler if we like distributed first and then like found the derivative?
It wouldn't be wrong. Eventually, even if you distribute it, eventually you'd have to apply the product rule anyway. So, I mean, you're not necessarily making your life easier. Because eventually you're going to have to multiply this p by that v, and you're going to need a product rule there. So, I mean, whatever. I don't necessarily recommend one over the other in this case. So do whatever feels right as long as it's actually correct. Not really in the mood to do dpdv. Let's just say dpdv is similar. I'd practice it if I were you, but not gonna go over it. Okay. Because what I want to talk about is another method entirely. Well, not entirely. Again, it's not really anything new. It's just we're going to combine two things that we already know how to do to sort of make our lives easier in some cases. In some cases. So the next topic I want to look at is called logarithmic differentiation. Let me kind of ease our way into this with a motivating example. How would you find the derivative of x to the x? That is the question that we are considering at this point. How would you find that derivative? X raised to the x part, what would you do? That's a variation on this technique, not exactly what I'm going to show you, but I'll actually mention that at the end. It's important that you first realize that the power rule does not apply, right? That's the first step. Realize that the derivative of x to the n equals nx to the n minus 1 would not work in this case because our power is not a constant. Okay? So this doesn't fit the template. Okay? You also should recognize that we do know how to differentiate a to the x. What is that? Yeah? Yeah? Right. A to the x ln a do not apply. Okay, so that's the first rule. So if you're thinking of trying to use an easy formula here, you are kind of out of luck. We do not yet have a formula to deal with this guy. It's very important that you realize that one reason why you should know these rules very well and why I ask you on quizzes all the time to repeat the rules is because you need to use them to judge whether you can apply them to solving certain problems. These do not apply. Power rule does not apply because the power is not a constant. This rule does not apply because the base is not a constant. We know how to deal with it if the base is a constant or the power is a constant, not both at the same time. So now we might want to consider, well, if none of the rules we have so far can deal with this, how would we deal with it? Here is one way. Set y equals to this function, and what I'm going to do is I'm going to log both sides. Right? Assuming my y is greater than 0 and this is valid, my x is greater than 0. Okay. This is why it's called logarithmic differentiation. You just take the ln of both sides. Now, that's pretty useful because logs allow us to simplify someone like that. The power can now come down to be a constant, well, a factor. Now what I can do is I can differentiate this implicitly. Derivative of the left side, y prime over y. Derivative of the right side at this point is something that we have a rule that can deal with, the product rule. This is x times ln of x. Differentiate the x, leave the ln, plus leave the x, differentiate the ln. In other words, I have y prime over y is equal to 1 plus ln x. This means that my y prime is equal to y times 1 plus ln x. And this means that my y prime, the y was the original function, it's x to the x is 1 plus ln x. And that is how we would define the derivative of that guy. So this describes the process of logarithmic differentiation. You might even realize that we actually used this kind of maneuver before. I just didn't tell you what we were doing at the time. We actually used a process similar to this to derive the power rule actually. If you can go back on that day where we derived a bunch of the rules all in one class, we actually use this maneuver already. It actually has a name. It's called logarithmic differentiation, and it is so named because we do it by logging both sides of an equation. The point of doing this is to simplify something. So if we have a power that we don't know how to deal with, or something is otherwise as complex, we can use logarithms to simplify the situation, because we know logarithms turn powers into products, they turn products into sums, they turn divisions into subtractions. A logarithm can move down the complexity of the operations. And so if you're able to take a logarithm of both sides of an equation, that can actually simplify things computationally by a lot. So this leads to the process of logarithmic differentiation, or log differentiation. So if you have y equals f of x, where f of x is greater than 0, you may find y prime by going through this process. 1. Log both sides, right? That would give you ln of y equals ln of f of x. The idea being we would be able to simplify that right side to get something easier to deal with. 2. You differentiate both sides implicitly. 3. Well, 2 I'd say simplify. Let's put that as a step on this one. Simplify the right side. 3, differentiate both sides implicitly. Right, this is the whole point of doing this in the first place, so you can simplify stuff. Let's put that out as a step on its own. Differentiate both sides. Implicitly, and then at the end of the day, you solve for the y prime. Right? Where it would always, in this technique, it'll always multiply, it'll always turn out to be you multiplying the original function by whatever's on the derivative of the right side. Right? So you can always actually think of the answer for something like this would be the original function times f prime over f, whatever that will happen to be. Now, this guy is useful in, I already showed you one situation, but I want you to appreciate that this can make our lives easier, even in cases where we already do have rules that will simplify things for us. This is useful. So you won't always do log differentiation, but if you're considering if one problem is particularly tough and you want to look at it and you want to know maybe log differentiation will work here, there are some things you can look for. This is useful if one, we have powers we don't know how to deal with. Again, if the power is a constant or the base is a constant, we have a formula that deals with that case. But what if both are variables and the power is particularly nasty maybe? You might consider using log differentiation. 2, applying previous rules. Like the product or quotient rule. Would be highly annoying. I'll give you an example of that. Example. What if you had y equals this guy? That's not nearly as annoying as I could make it, but just to give you some appreciation here, and you wanted to find y prime. Now technically, what we've learned so far before log differentiation can handle this. It's just a matter of applying the quotient rule. So one thing divided by another. But of course, if you look closer, whenever you're differentiating the top, you would need the product rule, because you have to have this times that. Then, if you're differentiating this and that, you would need the chain rule. So it's like you're applying the quotient rule, but inside the quotient rule, you have to be applying the product rule. While applying the product rule, you have to be applying the chain rule. That is what I call highly annoying. So, the question is, how do we make it less annoying? Log both sides. Because logs turn divisions into subtractions, they turn multiplication into additions, they turn powers into products. That kind of would make it a lot easier. So what I would do is ln both sides. Now what would this side become? Yeah?
So it would be three over four ln. Never mind.
This 3 over 2 is only applied to here.
Would be 1/2 ln x plus 3 over 2 ln x plus 1 minus 7 ln x squared plus 1.
That's what the right side would become. Now sure, I had one term, it's now split into 3 terms, but look at these individual terms. Those are super easy to find derivatives of. So now, by differentiating both sides, I would get y prime over y on the left side, and on the right side, this just becomes 1 over 2x plus 3 over 2x plus 1 times 1, chain rule, minus 7 times this, put its derivative on top by the chain rule, u prime over u. And so this would mean our derivative is, I'd move the y over, so it's the original function. So the y times this guy, 1 over 2x plus 3 over 2x plus 1 minus 28x over 2x squared plus 1. And of course, if you combine the 3 fractions here, multiply this out, and combine it all into 1, that huge mess you would get is what it would look like had you went and did the quotient rule. You can kind of appreciate after doing that how much pain you would have gone through to be able to do that. But this was relatively easy. So now I just want to talk about a slight variation on this method, which Jhevon mentioned, which in the solutions to the bonus on the test that I posted, use that method. Sometimes you don't want to go separately and set y equals to this and then log both sides and blah, blah, blah. You can kind of do it in a more contained form. So an alternative here is to recall this important thing, that an expression I can think of as e to the ln of that expression. Right? So that was one of the log rules that we covered. And by the way, I knew I could do log differentiation here because the radical x has to be positive. If it was 0, we didn't need it, we just use the power rule, but otherwise it works. But anyway, we have this rule. This allows us to, if we have something, this allows us to put an ln in front of that thing by a simple rewrite. Okay? So if I were to look for, again, going to the first example, just so you can see an easy application here. if I was asked what is the derivative of that, I could actually rewrite this. Oh, well, that's the derivative of this. Now, that allows me to use the powers of the logarithm to attack the x to the x power without really setting up a new equation and logging both sides. I can just rewrite. Well, that's just equal to the derivative of e to the, I can apply the log rule in the power. And now we know how to differentiate e to something. Well, it's the derivative of the power times the original function. Derivative of the power, that's the product rule. Differentiate the x, leave the ln, plus leave the x, differentiate the ln. So again, we end up with 1 plus ln x times x to the x. Where this is your x. So that kind of ends what we want to do with implicit differentiation, and now log differentiation, which is just a nice technique that allows us to break down functions into simpler ones. And I think we'll end there.